Well, welcome to our journey into number theory. These are just a few little exercises connected with chapter 3, section 5, with the questions 18 through to 20. And they're going to make use of the the divisor to sum identities, in particular the second one. So for the first one, we're asked to prove this particular fact here. And it follows quite nicely, in fact, from using that identity. So I put up here that this is our divisor to sum identity, number 2, that says if you've got the sum n less or equal to x f of n and sum d divides n g of d, then you can rewrite that sum in this form. It's a slightly obscure looking result, but it actually is quite useful. So we're starting off with this here, and we're simply going to write x, the floor of x over n, to be the sum j less or equal to x over n, and then we put a 1 there. That now puts it in this form, and so I can turn this back into a sum of this form, and the f here is 1, so I can simply plug this back in and it turns into the sum n less or equal to x sum d divides n mu of d. And of course we know that this sum here is in fact, this inside sum is 0 unless n is 1, in which case it's 1, and so we just get 1 as our sum. The second question was to do the analytics for n to the alpha and also for sigma sub alpha, where the sigma sub alpha is the alpha power of the divisors. So you take the sum of the alpha powers of the divisors and to develop that. And part C was to obtain this sum for log squared of n less or equal to x. So we simply, for this first one, we're going to simply apply our formula for approximating these sums by integrals. So we integrate t to the alpha, and then we get some constant which will be dependent on alpha plus big O x to the alpha. This integral is easy to work out, of course, and this is just a constant depending on alpha, so I can bury that in here and write this as x to the alpha plus 1 on alpha plus 1 plus big O x to the alpha, which is as one might expect if you think about the various sums of this shape. For sigma alpha of n, which is defined to be the sum over the divisors of n of the alpha power of the divisor, then if we want the sum of that, then we get another double sum. And now I'm just going to use the first divisor to sum identity, and I can rewrite this combination here in this form. Now, having done that, we can then, we've already worked out what this is in part A, so using part A I can just plug in I can replace the x with x over n, and so I get this expression here using part A. And finally then, just simplifying this, we can take out this term, we get left with sum 1 on n to the alpha plus 1, plus we're going to get big O sum n less or equal to x to the alpha on n to the alpha. We can now apply our approximation formula for this sum here by using an integral, so we just integrate 1 over x to the alpha plus 1. We end up with this expression here, plus we're going to get zeta alpha plus 1 plus big O x to the minus alpha, plus, so that's for the first term, that's replacing this with our usual formula. We've had this one in the lectures, plus big O, again we can approximate this using an integral, so we end up with this expression. We get this. Now the whole point about the big O notation is you can sweep everything under the carpet and get rid of it, so all we're going to get then is in fact the this term here, the zeta alpha plus 1 times x to the alpha plus 1, all divided by alpha plus 1. That'll be the dominant term, and everything else is big O x to the alpha. Now for part C, we're looking at log of squared of n, sum n less or equal to x. So again, we're just going to apply our integral approximation. So there's going to be the integral from 1 to x log of t squared dt plus a constant plus big O log squared x. And we can integrate this thing by parts, which I do here. Copy that down. So this is just integration by parts. Plug in the endpoints and subtract here. I get x log squared x. The log of 1 is 0, and then I integrate log t. I get t log t minus t from 1 to x, and I just substitute in, and I'm going to get x log squared x minus 2x log x plus 2x, and then all the other terms will be big O log of x squared. Finally, question 20 is just a little counting problem. It says, suppose we have a strictly increasing function from z plus to r, where the f of 1's between 0 and 1, n is a positive integer, and we're going to set m to be the floor of f of n. And we want to prove this interesting looking sum here, so we want the sum of the floor of fj's plus the sum of the floor of the fj inverses. And we want to show that's just m times n. Plus d. In fact, d turns out to be m. d is the number of lattice points on the graph of f. And then we want to use that to find a formula for this sum. So once you draw a picture, it becomes a lot clearer. So what we have is here, I'm going to take a rectangle with one corner a half f of a half, and the other corner up here is at f of n. We take this rectangle. Here's my function f, which is increasing, and f of 1 is less than 1. So this first sum j equals 1 to n of the floor of f of j, that counts the number of lattice points in this region I that are either on or below f of x, because it's just counting the lattice points in here. There won't be any lattice points in here because f of a half is the height here is going to be less than 1. So the other sum, j equals 1 to m, f inverse of j, take the floor. This counts the number of lattice points in this region j, which is above or possibly on the curve. And so when we add these two sums together, we're just going to get the area of this rectangle, which is m times n, but we've counted the points on the curve twice, one for each bit. So I have a plus d here, where d is the number of lattice points on f of x, because it's counted twice, and this d, in fact, of course, is just, turns out to be just m. It's the floor of f of n. So applying that to, we take the function f of x as x cubed, and f inverse is x to the third. Then we can use the formula we've just derived to get this sum here, and in fact I need a floor here, and that's just going to be equal to what we had before. This is mn plus the d, or m, and then minus the sum of the cubes. And the point is we can evaluate the sum of the cubes. It's easy. So this is just n times m plus m minus 1/4 m squared m plus 1 squared. And you might like to check that. You put, say, n is equal to 27n. You might like to check that this actually gives you the right number of, or right solution there. So that's up to question 20, and that's all for this section.